afternoon. Oh, it's working? Yeah, excellent. Hello, good afternoon. Thank you all for showing up. I'm going to give you a presentation about DNSSEC and about Kaminsky's cache poisoning attack. Let me just introduce myself and my organization. I work for SURFnet, which is the National Research and Education Network in the Netherlands. We connect all universities, polytechnics, etc., which is over 180 institutions in the Netherlands, and we have some 1 million end users connected to our network. And for this project on DNSSEC, which we've been running within our organization, I've been cooperating with Rick van Rijn here on the first row, who is self-employed and works for Open Fortress. Now, what I'm going to tell you today is something about cache poisoning. So what are the security risks that are in the DNS today? I hope you've all seen Bert Hubert's talk yesterday, which was an excellent overview of all the attacks that there are on DNS. Then I'm going to talk to you about DNSSEC on a high level, dive into some detail, tell you about what the status of DNSSEC is on the internet today, and then have a look at some criticisms, some alternatives, and then I'm going to tell you what you can do to improve the security of the internet. Now, let's start with DNS. What do we actually need DNS for? What do we use it for? Well, actually, DNS are the road signs for the internet. We need the DNS to tell us where we need to go if we want to communicate with our bank, for instance. And it's been known for years that there are vulnerabilities in DNS. One of these attacks is called cache poisoning. DNS works by using UDP packets, and I can really easily spoof a UDP packet. And for instance, I can trick a DNS resolver into believing that I'm actually sending him a valid answer to a query that he sent. So I can be a rogue responder, and I can just send lots of spoofed UDP packets to a DNS resolver. And if I'm quick enough, if I give him what seems to be the correct answer before the real answer arrives, then that spoofed answer will end up in its cache, and it will end up being served out to all its end users, which, if you are a large ISP, can be quite a number of users, as Bert Hubert told us yesterday. Now, these attacks that have been known for years were possible, but they're really hard to do. You needed to, for instance, either wait for a resolver to start querying for an address, or you had to wait for the time to live on an answer that it had in its cache to expire. So it was really nasty. You could be tricked into going to something that was really not your bank. So the value of the road signs on the internet was degrading. And then last year, Dan Kaminsky, who had a talk here yesterday, published an attack at the Black Hat conference. And he made matters a whole lot worse, because instead of actually having to wait for a resolver to take initiative or having to wait for the TTL in the cache to expire, you could just go at it, keep firing rogue packets at the resolver and actually hack it at your leisure. Because what you would do is you would ask the resolver, query it for a name that you're quite sure that it doesn't have in its cache. And then take all the time in the world to spoof some answers, and if you failed to hack it, you would do that again with another name that you know it doesn't have in its cache, so you use a name that you know doesn't exist. Now, what does this attack look like? First, we need to take a look at a UDP DNS packet. Now, there are some things in here that are interesting. There is the port that the query was sent from and that I need to reply to on the to the host that is asking me a question. And there's something in there that's called a query ID, which is actually authenticating that this is the real answer to a question that the resolver asked me. And there is some extra information in this packet. DNS is very convenient. It helps you along. It helps the resolvers along to get extra information so that it works efficiently. So there are some extra records. If I get an answer, and this is an answer to a query, I asked an authoritative server, what is the address for www.surfnet.nl? And it's sending me an answer, and it, along with the actual answer, which is the IP address is 194.171, etc., It also tells me that for the surfnet.nl zone, the authoritative servers are ns1, 2, and 3.surfnet.nl, which is really convenient. And to make my life even easier as a resolver, it sends along the IP addresses of these 3 servers. So what happens now, if the resolver receives such a packet, it will not only cache the answer for www.surfnet.nl, but it will also cache the answers that are in the additional section, which is the IP addresses for the name servers. So the next time someone asks for an address in the surfnet.nl domain, for instance, mail.surfnet.nl, it already knows which name servers to query for this answer. So how can I attack this? Well, I'm now going to show you the Kaminsky attack in action. I have a rogue responder somewhere, and it's going to query a vulnerable resolver by asking it for a name that it knows will probably not be in the cache. So it's going to ask for a nonsense host name, so 12345.piggybank.domain. What the resolver will do is send a query to the root server and then on to the top-level domain servers, etc., to find out if they can help it along to find the answer for what is the address of 12345.piggybank.domain. The servers that it queries will tell it, well, you need to go to the piggybank authoritative name server. So it sends the piggybank authoritative name server a request which has a query ID and a source port, etc., and says to the authoritative server, can you tell me where can I find 12345.piggybank.domain? Now remember, that will not exist, but it takes some time for the authoritative server to answer. Now, at the same time, the rogue responder will be sending lots of UDP packets to the DNS resolver, supplying answers to the query that it actually sent to the resolver. So it's going to say, I know the answer for the question that you've just asked. 12345.piggybank.domain can be found at this and this address. And it will put a query ID in there. Now, as you can see, the query ID that is in the answer from the rogue responder doesn't actually match with the query that it sent to the authoritative server, so the resolver is going to discard that because that is not a valid answer. But it can send lots of packets, so the next packet will have query ID 1234 in it. That doesn't match. But then it sends a packet that matches, and what happens now is that the DNS resolver will actually accept this as a valid answer. And what is in that packet will end up in the resolver's cache. Now, you can ask me what use is it to spoof the address for 12345.piggybank.domain. That's not bad. Nobody's going to query for that. Well, what's in this answer packet is some nice additional information. What I also put in there are the name server records for the piggybank.domain zone. So I'm going to put in there that the address for ns.piggybank.domain is actually my rogue authoritative server, and that really, if you want to know something about piggybank.domain, you need to ask me and not ask the valid authoritative server. And because I beat the real authoritative server with answering the question, whatever it answers will be discarded because the resolver already has an answer. Now, what does this look like if I have a look at the answer to that query? What you can see is that there's an answer, abcde.piggybank.domain. I used 1234, I think, but whatever, has an address. That's not really of any value. But I can point, in the additional section, I can point to rogue authoritative name servers, which are marked here in red. And to make matters worse, I give them a really long time to live. 604, 800 seconds is 1 week. But I could make it a year if I really wanted to. So that means that anybody who is now, as an end user, going to query this DNS resolver, and keep in mind, if that is your ISP's DNS resolver, you have a problem. It will ask, what is the address for www.piggybank.domain, because the user wants to do some internet banking. Now, what should happen is that the DNS resolver goes to the root and TLD servers and to the proper authoritative server. But because it's already cached, the address for the name servers that are authoritative for the piggybank.domain zone it will send a question to the rogue authoritative server, and it will say, well, you can find www.piggybank.domain at this address. And it will send that answer back to the vulnerable end user. And the worst part is the end user can't tell the difference. He can't tell that he's been given a wrong answer because it looks completely valid. It comes from the cache, it comes from its ISP resolver, it's completely trusted, it's all fine and dandy. And what will happen, what could possibly happen is that the attacker would copy the site of the bank and only, for instance, replace the link which goes to the login page for internet banking. Now that is a really nasty attack. So actually, it's even worse. I can replace the road signs for a whole domain. So I can tell everybody who wants to do business with Piggy Bank that actually all their servers are mine and really you need to talk to me and not to them. So, is it all bad? Well, as Bert Joubert, who was also in the room here, explained yesterday, DNS queries are identified using a 16-bit number. But in the past, resolvers that were querying authoritative servers used sequential numbering. So it was really, really easy to watch some traffic going on and then spoof an answer because you could very well predict which query IDs were going to be used. And even worse, the first version of Windows XP always used query ID 1, and if it had to send out a second query at the same time, it used query ID 2. But then if it was ready, you'd go back to 1, so really easy to guess. And then you can add some extra randomness to this puzzle by sending DNS queries from a random UDP port. So the attacker would also have to guess what UDP source port to put in the packet. But what if you have a network address translation firewall between your resolver and the internet? That very handy firewall will say, oh, I've got a UDP packet which I need to translate, and when the answer comes back, I need to translate it again. So what I'll do is I'll put a nice, easy to remember UDP source port number in there, say 1234. And, well, if there aren't any other UDP packets, the next time I'll use 1234 again. Really convenient. So people have been patching since Dan published his attack, have been patching their servers. I think most people on the internet now have updated their resolvers, at least they should. Check with your ISP whether they've done that, because otherwise you're vulnerable. And that's all fine and well, but people have been doing some research. If I patch a server, does that really protect me against this attack? And what they find out is, I've been talking to the guys from the Czech top-level registry who've recently rolled out DNSSEC. And they said, well, we did some tests with unpatched bind. It takes 3 seconds to poison it. And we've done some tests with a patched bind. And actually, if we have a dedicated link to it, so not a real-world situation, but anyway, if we have a dedicated link, we can actually spoof a patched server within 1 to 11 hours. And Bert Joubert in his talk yesterday showed that, well, you can really see those attacks going on because you'll be sending lots of packets to the resolver, and actually the resolver will die because you're flooding it with packets and it will just expire. But what you can do is, an attacker has all the time in the world, because remember, he can keep on sending packets, and the only thing he has to do is he has to send the one packet that makes him win. And if that takes 6 weeks, then he has a really, really good chance by sending just 100 packets a second to attack a resolver. And he has a 50% chance of succeeding if he does that for 6 weeks. So at this year's HAR, we had a challenge for you. We put up some posters and there was some information on the wiki. We challenged you to hack a few resolvers that we prepared especially for you. And as Bert explained in his talk yesterday, it was very unlikely that you were going to succeed, because either our resolvers were going to expire because of the flood of packets that you were going to send over the 10 gigabit link that we have here, and otherwise something called BCP38 has been implemented, so you can't actually spoof the source address in a UDP packet anymore if you're transmitting from the HAR network. But that didn't stop you guys from trying, because as you can see in the graph, there's a little green spike on Thursday evening. Some people tried to actually attack the cache that we have, but no one succeeded, so unfortunately I can't hand out a pie. But we're very sure that if we had 6 weeks of this excellent conference here, that someone would have won the pie, and I'd be happy to give it to you. Now, we've had a look at all these vulnerabilities that are in DNS. So is there maybe a solution that we can implement to actually mitigate this attack? Well, it turns out that there is a solution available today, and it's called DNSSEC. Many of you may have heard of it. Some of you may know the details of it. I'm going to tell you a little bit about that now. Now, DNSSEC was developed by the IETF, and it's been actively developed since the mid-90s. So it's been going on for a long time, and nothing much has been happening with the deployment up until the point that Dan published his attack last year, when suddenly some people realized, hey, maybe this is something we need to do. Now what DNSSEC does is it makes it possible for you to check whether you've received a valid answer, because actually there is a digital signature on the DNS records that you can get back, and you can validate this digital signature, and if it fails to validate, then you've been given a wrong answer. It's also important to note what DNSSEC does not do for you. It does not provide confidentiality. If I'm looking at, if I'm creating a resolver and I'm really interested in www.nakedwhatever.com, people can still see this. It doesn't provide me any confidentiality. And it does not protect me against other threats, such as denial of service attacks, which are also a major issue. I mean, if the DNS doesn't work, the internet is broken, at least that's what users think. Actually, DNSSEC makes this a whole lot worse, because the packets, because the digital signatures are in the answer packets, they are a lot larger. So actually you can scrap the D in distributed denial of service, because I can now attack a server from one end system, because the packets are such a lot larger. Neither does it prevent people from making typing mistakes in their DNS zones. I mean, it doesn't guarantee that the person who's actually typing in the records doesn't make any human errors. Now, I'm sure all of you know what RSA is, so I can probably skip over this. But just a quick recap. DNSSEC is based on public key cryptography. So I use a private key that I keep for myself to sign the records. And I have to publish a public key that people can use to verify the signatures on the packets that I'm sending out. Now, how are these keys used? This is not something that is specified in the standards, but it is common operational practice at the moment. People are using a two-tiered key model. There's something called a key signing key, which is a rather large key for security reasons. It is something like a 2048-bit RSA key, which has a long validity that you can use for a year or longer. And they use it to sign a second key, which is called the zone signing key. Now, this is the key that I actually use to sign the zone. Now, signing in DNSSEC takes place at the zone level. I either sign the whole zone or I don't sign it. There are some exceptions to this, but that is basically the idea. And because some zones can be really large, I want to be able to sign a zone quickly, because it might be changing often if I'm operating something like a TLD or I have dynamic DNS updates. So I need a smaller key to be able to achieve the speeds that are necessary to keep re-signing such a zone. So this zone has a much shorter validity, because really 1024 bits RSA isn't that secure anymore. And I use that key to sign the resource records. Now, what happens if I sign my DNS zone? What does it look like in my zone? Well, I get some extra resource records, because actually, as I told you before, I need to share my public key with the rest of the world, otherwise they can't validate my answers. So I need a DNS key record, which actually shows you the public key that I use to sign this zone is this and this and this key. And actually, I also need to be able to do something with delegation. I'll get back to that a little bit later. So there's also a DS record, which my parent zone can put in its zone to actually show that it can certify that my key is actually the valid one for my zone. Now then, there's an extra record that you will be getting back if you query and you ask for a DNSSEC answer. You will get an RRSig record, which is the signature on the resource record or research records that you requested. And finally, I need to be able to do authenticated denial of existence. So remember, those of you who know DNS, if you ask it for an answer and it doesn't know the answer, it says NX domain, I don't know the answer to the question you're asking me. Well, in DNSSEC, you really want to be able to tell the end user that you don't know the answer, and you actually want to prove that you don't know the answer. So to do that, you use something called NSEC or NSEC3. Now, if you do DNSSEC, your zones will become quite a bit larger. Now, if you have a small zone, that's not an issue, but if you are operating a TLD, that actually has quite an impact on your operating procedures, because you need more memory to store your zone, you need more bandwidth to serve it out, etc. Now, what actually happens if I want to validate a DNSSEC response? Now, in this example, I'm using the www.nist.gov, because actually the US government mandates the use of DNSSEC since late last year. And I can actually query nist.gov, and I will get a signed answer back. Now, how do I validate this signature? Well, I need to know what key was used to sign the nist.gov zone. Which in this case is indicated in the RRSIG answer. The first bit says 156, that's the key ID that was used to sign that record. So I need to look up that key. Now, whose job is it to do that? Well, your resolver should be checking these answers. But how does it find the key? Well, it can query for the DNS key record, but how does it know that it can trust that key? I mean, I can publish a zone, put any public key in it and say, well, that's my key. And I could spoof that. So how do I know that I can trust the NIST.gov key? Well, I'm going to answer that in a bit, but first I'm going to show you a little bit about the current state of deployment, because that is necessary to be able to explain the rest of my story. At the moment, DNSSEC is deployed on some TLDs, some smaller and medium-sized countries. Some TLDs.org has recently been signed, I think in June. And the US government has actually signed the .gov domain since January 1st this year. But what's more important is that some really large TLDs, .com and .net, VeriSign has announced that they are actually going to sign these big TLDs. And that means that, well, something in the region of 65% of all domains, it will be possible to deploy DNSSEC on them once this has been done. And they have actually committed themselves to doing this hopefully before 2011. And as Dan Kaminsky mentioned last night, it would be really convenient if the root would be signed. Because, well, actually, if the root isn't signed, how am I going to build up the trust? Well, the good news is that the US government and ICANN have announced that they're going to do their very best to sign the root before the end of this year. And that's been quite a strong commitment, so I'm hoping that they won't crawl back and say, well, it's turned out to be really hard and we're not going to do it. The bad news is that there's a lot of politics involved there. Many people are either opposed to the root being under control of the US government or VeriSign doing the operational work on that. But I'm hoping actually that this will take place. On the other hand, many TLDs and many CC-TLDs have not announced what they are going to do with their zones. For instance, the Dutch registry, SIDN, is thinking really hard about DNSSEC, but they still have some operational issues with that, so they haven't announced anything, and I'm sure that's true for many of the TLDs in your countries as well. So, let's go back to the question, how can I validate the answer that I got when I queried for www.nist.gov? Well, the NIST.gov zone has been signed. I hope you can read it, but I'm going to talk you through it anyway. The NIST.gov zone has been signed using a private key, and the public key has been published in the zone. And actually what they have done is that they have supplied a hash of this key that they used to sign to their parent domain, which is the .gov domain. And what .gov will do is they will publish this hash in their zone, and then they sign their zone as well. So what they're saying is, we really trust NIST.gov because we actually assert that this is the key they use to sign their zone. So instead of every resolver having to negotiate trust with NIST.gov and with whitehouse.gov and with whoever, they can just decide to trust the US government and trust the .gov domain. Now, what would be really convenient if the root were also signed, because then the root could say, hey, we trust the US government, they use this and this key to sign their zone. So actually all I need to do is trust the root, and I only need to trust one set of keys to express trust in the complete DNS infrastructure. Now, unfortunately, the root hasn't been signed yet, but if that happens, that becomes possible. Now, because that hasn't happened yet, at the moment we are faced with a situation where we have islands of trust. The areas marked yellow in this picture are changed that are signed. .org is signed, .gov is signed. Well, SurfNet isn't actually signed, but I needed an example. So the top of these chains, we call those trust anchors. So at the moment, if I want to validate DNSSEC answers, I need to know all these trust anchors. I need the key to know the public key for .org. I need to know the public key for .gov. So how do I find these? Because if I want to be secure today and if I want to validate the signed answers that I get today, what do? Well, I need to find these trust anchors. And as it turns out, it is really hard to manage these by hand. And some people have tried to help us along, because IANA has made HAR available, which is a set of trust anchors for all the top-level domains that have signed their zones. And ISC, which are the people behind the bind name server, have introduced something that they call DNSSEC leukocyte validation, and that is actually a repository that that you can submit your public key to, and that a resolver can query. I'll tell you a little bit about that in the next slide. Now, the problem with this is that there is no standard way to trust these repositories. For instance, you can see IANA has secured their site using SSL, HTTPS. So if I trust SSL, and if you heard Dan's talk yesterday, that's a bit questionable. But if I trust SSL, I can use that to trust the information that I get from IANA and the ITAR repository. ISC is actually using DNS for the leukocyte validation. So they're using a DNS server themselves. And I need to trust the key that they use to sign this DLV domain. And actually, I need to download this from an unsecured website, and I need to check a PGP key that is on there. So that makes it, and remember, these keys all have a limited validity. They are either valid for maybe a year, or in case of a certificate, maybe 3 years. But after that time, I will need to download new trust anchors, because either the trust anchors have expired, or the trust on the trust anchor repository has expired. And I need to keep up to date if I want to stay validating. Now, the good news is that these are all interim solutions. Once the root is signed, hopefully we won't need these anymore. Now, just a little bit about DLV. They put the public keys at the top of the trust chain, so the trust anchors into a repository. And actually, if a resolver wants to query a domain and it wants to validate the answer on that, it can ask the DLV, well, do you have a trust anchor for this query that I have? The downside of that is that ISC actually receives all the queries that I do on my resolver, which is a bit of a privacy issue. So keep that in mind if you want to use DLV to validate DNSSEC answers. Now, I made this nice slide with lots of colors for some of the managers within an organization. And what you can see is that, well, this is a standard graph that anyone can use. It shows you where we are now, 2009. I hope you can see it. Is somewhere over there, and we are in the early adopters phase. But actually, I'm a little bit more optimistic at the moment, because this year, many people have started working on DNSSEC. Suddenly, people are saying, hey, we're going to sign the root before the end of the year. And VeriSign is going to say, well, we are going to sign .net and .com. So actually, I moved 2009 a little bit forward, and I'm a little bit optimistic about where we are now. I'm sure not everybody shares my optimism, but hey, hopefully it's going to happen a little bit sooner. Now you're going to ask me, is there no criticism on DNSSEC? Well, Bert Hubert, who gave a talk yesterday, has been a very vocal critic of DNSSEC, and he said, well, DNSSEC, it's the string theory of the internet. It has a cult-like following. It will be ready in 6 months, etc., etc. And well, really, it is something nasty and it's horrible and it's hard to do. And actually, he's right. DNSSEC is hard to do, but even the critics agree that DNSSEC is the only solution available at the moment to mitigate attacks on the integrity of the DNS. Now that doesn't mean DNSSEC is perfect, and it's really hard to do because you need to manage keys and you need to roll your keys when they expire, and you need to talk to your parent domain, which there are no standards for at the moment. So it's really hard to do, and actually if you mess it up, your zone disappears from the internet. So your domain could disappear, which is really, really nasty for people, because at the moment DNS, although Bert said it's really hard to implement, once it's been implemented and when you are operating it as a system administrator, DNS is actually very forgiving, because you can make lots of mistakes before your zone actually goes down off the internet. Now I'm also responsible within SurfNet for our DNS infrastructure. And I have a lot of our connected institutions who make small and larger mistakes. Some of them have actually blocked both UDP and TCP on their authoritative servers, and which basically means that no one can reach their authoritative servers, but because we run a secondary for them and they allow us to do transfers, their domain is still on the internet. And I have a really hard time explaining to them that, well, DNS is a public thing, so you should expose your servers to the rest of the world. And they say, no, that's not safe, we can't do that. So DNS is very forgiving because there is this redundancy built in. And with DNSSEC, because it is much harder to manage, I can break it more easily, and if I do that, that will lower the acceptance of DNSSEC, and actually it will be dangerous because it's a dangerous tool in the hands of people who don't know what they're doing. So in my opinion, what is really stopping DNSSEC from being rolled out on a large scale is good tools, because actually if you have a tool that you can tick a box that says, well, turn on DNSSEC for my domain, and I don't have to worry about all this key stuff, and I don't have to worry about rolling keys and signing zones and sending data to my parent zone, then it could be really easy, and it will make the internet a whole lot safer. So are there tools available? Well, at the moment, tools are in the making, some tools are available, but you need to really know what you're doing if you're going to deploy DNSSEC at this point in time. The good news is that many people are working on good tooling. We as SurfNet support a project which is called OpenDNSSEC. Please have a look at it later. I'm plugging it here. Which is actually an open source DNSSEC signer, which should make it really easy for you to sign your zones. There are commercial appliances available from Secure64 and Accelerants. There are other open source projects like ZoneKey tool, which makes it really easy to sign your zone. And actually, Bert Hubert from PowerDNS announced yesterday that he's working on PowerDNSSEC, which he thinks should be a turnkey solution to deploy DNSSEC. Because, I mean, if your product is easy to use, which I've been told PowerDNS is, then PowerDNSSEC should be easy too. Now, for resolvers, the picture is a whole lot better. Actually, most resolvers that are around today, at least the most widely used ones, are actually capable of doing DNSSEC validation. For instance, there is Unbound from Nelnet Labs and Bind9, which out of the box support DNSSEC validation, and they can work with these interim repositories like ITAR and DLV. And actually Microsoft has announced that they're going to include DNSSEC in their upcoming 2008 Release 2 and Server 7. They haven't really specified what they're going to do with DNSSEC, just that they're going to do something with DNSSEC. So let's hope it's not something that breaks stuff. Now, another question that you could ask is, are there really no alternatives? Is DNSSEC the only thing we can do to mitigate these attacks? Well, we could always keep patching our software, and we could always keep introducing new ways to counter these attacks, like we've done by introducing port randomization and by introducing query ID randomization. That could help us, but that's an arms race. We're fighting against people who have a known attack that works. And remember the 6 weeks attack that Bert talked about yesterday, I have all the time in the world. So if I make it harder by adding an extra bit of entropy to my UDP packets, well, maybe it will take me 30 weeks. I don't care. I want to spoof the answer to a major bank, or I want to be able to fool people in thinking that Microsoft stock is actually going up if I query the New York Stock Exchange site. We could use SSL or TLS. Well, as Dan Kaminsky showed yesterday, do you really want to use SSL? And DNS is a really lightweight protocol. Now, DNSSEC makes it a bit heavier, but using SSL would make it really heavy. So that's not really a solution. Now, there is TSIG and SIG0, which you can use at the moment to secure transactions between name servers. Now, could you use that? No, that doesn't scale because you need to share secrets between all the servers. So every resolver would need to share secrets with all the authorities that are out there, so that wouldn't work. Now, Dan Bernstein, who some of you will probably know from DJB, DNS, and QMail, has come up with his own solution called DNS Curve. And actually, I talked to him recently, and what he came up with has a lot of merit, and it's got a lot of really good ideas in there. But there's no wide-scale deployment. It hasn't been around long enough, and actually, if I want to download it, it's not available yet. It's just a concept. He's programming it as we speak, but hey, DNSSEC has been available for a long time. It's available now. Why not use it? And actually, he said to me that even though he's not a big fan of DNSSEC, he said, well, it's the only solution available, and it makes the internet safer. Why not roll it out? And finally, something is available that's called DNSSEC OX20, which says, well, hey, DNS is case insensitive. Why not use capital letters in some of the queries, which would add extra bits of randomness to a query as long as the authoritative copies the capitalized letters in the response that he sends back. So I create an extra secret between the resolver and the authoritative server. But is that really something we want to do? Because it works with almost all name servers, but not all of them. So with the ones it doesn't work with, we break a relationship. We break something that is basic infrastructure of the internet. And does it really protect the root zone, where we have really short answers like com and net? Does it really help if we capitalize the C of com? That introduces about one extra bit. That doesn't really help us, does it? So what I've tried to tell you today is, what does DNSSEC do for you? Well, you can go out to the world and prove that you actually own a domain and that the answers that you are giving are authentic. And if I get an answer from you, I can actually check that the answer you've given me is authentic. So I'm really talking to my bank, or I'm really talking to my insurance company, or whatever. I'm really talking to my university. So with DNSSEC, you can effectively protect yourself. So just a few more slides about what we have done. SurfNet is an innovation organization, and we actually, when something new is around, we have to play with it and try it. So what we've done is we've made all our resolvers DNSSEC validating. And we are, well, one of the first large organizations in the Netherlands who have done this. And what we see is that actually some of the answers that we get validate. I'm sure it's probably hard to read, but what it says on the left is that at the time that I took this snapshot, from the 350 queries per second that I was doing at that time, about 1.5 of those I was able to validate. And actually at the peak, I was doing some 500 queries a second, and about 5 of those I was able to validate. So that's 1%. That may not sound much, but that's more than the IPv6 traffic on the internet at the moment. So we're doing something. So what are we going to do? Well, we operate a managed DNS service for our institutions. And what would be more convenient than we make it possible for them to tick a box, enable DNSSEC on my zone. And actually their zone becomes signed. We're going to test appliances as they appear on the market, and we're going to tell our institutions about that, and that's something that you can do as well. And we're supporting OpenDNSSEC, which we hope will become a success, and will make using DNSSEC for you a lot easier. But what is more important is what you can do. The problem with DNSSEC, as I said, it's really hard. You are the people that know how to do this. You are the people that know cryptography. You are the people that know DNS. You are the people that know internet security. So please gather some knowledge on DNSSEC and be the person in your organization who actually prevents stupid people from deploying it and breaking your zone, and actually do it right. We've written a paper about this which explains the technical details of DNSSEC in little. There are some paper copies here in front of the room, but you can download it from the URL that you see here as well. You could update or reconfigure your resolvers to actually start doing validations, and it will really help if we get some data on what is actually happening on the internet. Are more people signing? So do I get more validated answers? And actually, if I start validating, does that break my DNS infrastructure? These are things that need to be deployed in real life to see if it actually keeps on working in a real life situation. And finally, you could make DNSSEC a purchasing requirement. Now, as Bert already explained yesterday, notorious problems are home DSL routers. They break lots of stuff about DNS. And I'm quite sure there's been some research from Nominet, the UK registry, that they break quite a bit of DNSSEC as well. So if you introduce new stuff, these really simple devices which have been made for the lowest cost are going to break. So have a look at those as well. And finally, I really want to encourage you to work on an open source project. Please either cooperate with Bert on Power DNSSEC and help him there, or go to OpenDNSSEC and test the software. We really need people to download the software and try it and tell us what needs to be improved. Tell us how it works for you. And what we really need at this point in time is an organization that has lots of small zones that they need to sign. Because the people that are cooperating in the project at the moment are top-level registries who have really large zones, and we really need to hear from people who have small zones. And if you have an interest in that, please come talk to me after this talk. So I would like to thank you for your attention, and if there are any questions, I think now is the time.
Hi.
Hi.
What may be a small issue that stands for a wide-scale deployment of DNSSEC is it's not a problem as such in the Netherlands, but in other countries you can only use state-licensed crypto. For instance, in the former Soviet Union, you can only use GOV. So that's what they're currently trying to tackle there.
Okay, let me just see if I understood your question correctly. What you're saying is that in some countries you can't use strong cryptography to sign your zone, so what would you need to do if you're in one of these countries? Is that correct?
That's what they're currently working on. Like you have the standard set of, AES and RSA, MD5, and that's currently a fixed set, and they're trying to find a way to allow for different crypto if, for instance, your country doesn't allow those crypto to be used.
Okay, yeah. Well, in the specification there's room for a lot of more algorithms, and actually there is already an identifier reserved for things like elliptic curve crypto. So, I mean, the protocol is extensible. Just go to the IETF and say, I need this new algorithm to be incorporated, and, well, you probably need to prove that it is a secure algorithm, because once you introduce this, the rest of the world will need to support it as well. So this will always have to be something of a standards track. But they're already thinking about this, and they already have identifiers in place for things like elliptic curves.
Yes. In order for DNSSEC to work, I imagine you need operating systems to support it and client-side applications, right? Which ones do and which ones don't support it yet? Or
okay. Well, in the end, it's going to be very important that the end user device is going to support this validation, right? Because you want to validate the whole track right until your home PC. But actually, at the moment, it's more important that the resolvers of your ISP support DNSSEC validation, because that makes the attack surface a lot smaller. They would have to poison the resolver in your end-user PC to break it if the resolver of your ISP is already doing the validation. And actually, it's a lot less feasible to attack all these end users than it is feasible to attack a large ISP, which is actually the party that I want to poison. But your question is valid, and actually there's a bit of an issue if I'm going to put DNSSEC validation in these end user appliances, because that damn home router is in between. And that is going to mangle some of the packets, and actually some of them die if you send them DNSSEC answers.
So you mentioned a project that makes it easier to use DNSSEC on Power DNS. Are you aware of any tools to make it easier to use on Bind? Is it still the de facto standard?
Yes. The zone key tool, which I mentioned, that actually works with Bind, and Bind comes with its own set of tools to do zone signing, so you can use those, but you really need to know what you're doing if you're using those. The way OpenDNSSEC is going to work is it's going to be something that's a bump in the wire. So I have a hidden primary, and I have a public primary, and I put OpenDNSSEC in between, and actually I do a transfer to OpenDNSSEC, it signs, and it does a transfer out to the public primary. So that's the way to do it.
Are there any mitigations in current DNSSEC supporting DNS servers to stop DNSSEC?
Sorry, I can't hear you. Can you speak a little bit louder?
Are there any mitigations in current DNSSEC supporting servers to stop DNSSEC making the DNS amplification problem worse?
Not that I'm aware of, no.
So basically, currently, DNSSEC supporting servers are really good targets for DNS
yes, they
amplification
are. Yeah.
attacks.
That's also what Bert mentioned in his talk yesterday. I mean, if you introduce DNSSEC, you are going to make servers more vulnerable to denial of service attacks. Yes, that's true. But it's always weighing, it's checks and balances. Do I need to protect the integrity, or do I need to protect the availability? And that's not a choice that I can make for you.
Okay, thanks.
Hi, thank you first for the presentation. It's really good. I'm wondering, it's a bit of a political issue, but if you're going to sign root CAs, isn't it a good issue to advance the speed of getting independent from the US government, for example, because otherwise there is a small organization which is dependent on the government, which hold the private keys to sign the whole route.
Yeah, well that is a... There are two things to think about here. Yes, the US government is in control, and that might be something that many people really don't like. And actually there have been some quite vocal expressions from countries like Russia and China that they're opposed to this, and which is understandable. On the other hand, what is the alternative? That is putting something like ICANN under control of the United Nations, which means it becomes totally unmanageable, because all these 180 countries are going to want to have their say, and they all have the right to veto any changes that you make. You have to think if that's really something that you want. Whereas now under the Department of Commerce, at least someone is driving it forward, someone is taking decisions, and someone is saying, hey, I'm going to be the bull in the china shop, and I'm just going to do it.
Yeah, it's really hard. It's a really political issue, but if there is going to be work done, maybe it's time to act now and not at a later stage.
Last year there was a petition by the Department of Commerce to ask, they presented a number of solutions for signing the root, and they asked people to comment on this and say, do you like this mechanism that we thought of, or do you, which one would you prefer? So actually they took the initiative to petition the whole world to come back with answers, and I'm not sure how many people responded to that. One of the issues is also who controls the keys. Does VeriSign control the keys that sign the root, or does ICANN control those keys? Which is also an issue. So
yeah, okay.
Please be vocal about this. Join the discussions if you're interested in it.
Yeah, absolutely. Well, thank you for your answers.
Okay. Yeah. One more question, I think. Yeah.
Yeah, thank you. I have a question. Well, designing a security protocol is not simple. And it seems like DNSSEC has touched the hard parts of cryptography. They have touched authentication, they have touched integrity, and they even touched PKI. But why the hell not confidentiality? Why isn't the request encrypted? So there are two questions. Why hasn't it been included in the standard to encrypt the request and the answer?
Yeah.
And is there any intention to encrypt in the future? Because quite honestly, that's what I want. If I serve to piggitits.com, I don't want anyone else to know that I've served to piggitits.com.
I understand.
And it seems like that's the easy path. Really, symmetric encryption is the easy path of cryptography. So why would they go through the effort? Please answer first, yes.
Well, that depends. I mean, if you want to have confidentiality and have encryption between the resolver and the client who is querying it, you need to share a secret between these two parties.
But they already do PKI. They already exchange public keys, so they already have
but
the means to exchange shared secrets, security.
You have the public key for the signed zone. But the entity that is sending you these answers doesn't have your public key, so it cannot encrypt a session key with your public key that only you can decrypt. So you need to put mechanisms in place to establish trust relations with all these clients that are querying you.
What you're saying is you have to exchange 2 more packets.
Sorry?
What you're saying is that you would need to exchange 2 more packets.
Well, you would need to do a lot of extra online crypto. The DNSSEC works offline. I can sign the zone in the background. And I can, if I have a really big zone, I can have dedicated servers to do that. But what you're saying needs to be done online. And that means that
it only has to be done between 2 peering DNS servers, so between the resolver and my querying server.
I mean, you can set up, you can use TSIG or SIG0 for that. You can set up a secure link to your resolver if you really want to.
Well, yeah, I could use IPsec, but we all know that doesn't scale.
Sorry?
And I could use IPsec, there are many other solutions, but we all know that they don't scale.
Yeah, but I mean, there are mechanisms in place to do that. But if you want to put this in an online solution, have a look at DNS Curve. Dan Bernstein has thought about this, and that's actually addressed in DNS Curve. But the answer that the solution that he's come up with doesn't actually scale for DNSSEC, because DNSSEC uses things like RSA, which uses a lot of your CPU power, and DNS Curve uses elliptic curves, which is a lot easier on your CPU. So that could work, but unfortunately that wasn't available when people started thinking about these issues. And that's actually not available today to download. So. And
is the DNSSEC community thinking about implementing confidentiality?
No, not that I'm aware of now.
Cool. Thank you.
Okay, thank you for your questions. Thank you. Yeah. Yeah. So if anyone.